Next speaker is Yoni Zohar. So the talk is entitled Bit Precise Reasoning via Int-Blasting, and it has a long list of speakers. I don't want to take all 30 minutes to read out the list of speakers, but Yoni will be presenting the talk.
Hello, can you hear me, Shankar?
Yeah,
Great, okay.
and we can see your slides also. Yeah.
Great, thank you. So yes, this is joint work with many co-authors, and I will also not spend the entire talk on reading them. I will say that it's about reasoning about bit vectors with an integer-based approach. So the general subject is bit precise reasoning, which is reasoning about bit vectors. Bit vectors are finite sequences of bits, zeros and ones. And when reasoning about them, we use variables that range over bit vectors, constants that are concrete sequences of bits, relations like equality and inequalities, and the inequalities can be signed and unsigned, arithmetic operators like bit vector addition, multiplication, and also bitwise operators, bitwise and, shift, etc. And we can also combine such formulas with logical operators. Now, all the terms in this framework are sorted or typed, which means that for every variable, for example, you know how many bits it has, you know its bit width according to its sort or type. And a prominent framework for reasoning about bit vectors is within SMT solvers, Satisfiability Modulo Theories solvers. And the state-of-the-art approach is called BitBlasting. In BitBlasting, you translate each bit of each bit vector to a unique Boolean variable. And then the operators are encoded using circuits. And this approach is indeed the state of the art, is very successful. However, it does reach some scalability issues, especially in the presence of large bit widths, like 256 bit vectors. And even with smaller bit widths, if you have multiplication or division, then you can also face scalability problems. There are other approaches that are alternatives to bit blasting, like MCSAT, model constructing satisfiability and local search, which I'm not going to talk about, but I will present an integer-based approach. When talking about integer-based approach, you have basically two options. If you write a verification application and you want to encode bit vectors as integers, you can do it in the application level or inside the solver. And we chose to do it inside the solver. Now, if you do it in the application level, then this is an eager encoding. You dump the formula up front, the integer formula. Usually, you need to abstract the bitwise operators because they don't have any natural integer encoding. You then use the solver as a black box, and the encoding itself might be application specific. There might be some considerations that were specific to your application. In contrast, when doing it inside the solver, the encoding can be either eager or lazy, and what I will show is an abstraction refinement scheme for the bitwise operations. You have more control over the behavior of the solver because you're doing it inside, and the solution is more general. Other applications can use it. And this approach of solving bit vector formulas by an internal encoding to integers rather than to Boolean logic, we call it Int-Blasting. And in the next part of the talk, I will show how do we do it. So basically, our goal is to take a bit vector formula and translate it to an integer formula. But to be precise, we also use an interpreted function. And the way we do it is that we go through an intermediate representation, an intermediate theory, which extends the theory of arithmetic, and from it we translate it to integer and uninterpreted function. So let's start with this intermediate theory. We call it integer plus I-end or arith plus I-end. I-end stands for integer end. So this is just nonlinear integer arithmetic extended by countably many binary operators. We call them I-end1, I-end2, etc., where the index, at least intuitively, represents how many in how many bits do you encode the natural numbers and then perform the bitwise AND. The semantic is just bitwise AND between machine integers. So let's take an example for I and 4 with inputs 1 and 2. To compute the result, we transform 1 and 2 to 4-bit vectors and perform bitwise AND on them. So the result is 0. Okay, so this is an extension theory of arithmetic, extended theory of arithmetic, to which we translate bit vector formulas, and from which we translate into integers and UF. So let's start with the first step, a translation between bit vector formulas into this extended theory of arithmetic. So basically, the idea is to translate bit vector variables to integer variables and constants to unsigned unsigned interpretation as integers. And the bit vector operators will be translated to integer terms based on the semantics of the bit vector theory, as specified in SMT-LIB. Translating bitwise AND is more difficult, and this is precisely why we introduce these operators, these I-AND operators, and some operators are eliminated using others. More formally, I'll present the translation itself. So we have a translation function, t-phi. The translation function is t, it accepts a formula phi, and it returns a conjunction c phi and lem of phi. C is for conversion, and lem is some lemmas that we need to add to the formula. So let's look at the conversion function. As I said, bit vector variables go to integer variables. We assume that phi is a one-to-one mapping between these types of variables. Constants are with the unsigned interpretation, and relations like equality, you leave the equality, just now it's equality between integers, and you recursively compute the conversion of the arguments. Now with inequalities, so unsigned inequality just translates to the ordinary inequality in integers, but for signed inequality, we need to do some transformation. So we use a function that we call UTS, unsigned to signed. And this function, let's look at an example. If the input for this function is 9, then what you do is you convert it to a bit vector with an unsigned interpretation. You get 1001. But then you can look at this bit vector with a signed interpretation, and then the result would be -7. So this function for the input 9 will return -7. And this function is definable in the nonlinear integer arithmetic. So we use this to handle signed comparators. Now for arithmetic operators, this is straightforward. It is done just modulo 2 to the power of the bit width. Specifically for logical negation, we don't need to take it modulo. We don't need a modulo operator. Div and model also handled similarly, just that in SMT, the semantics of division in bit vectors allows division by 0 with a specified value in this case. So we encode this using an ITE term. ITE stands for if then else. Concatenation and extraction can also similarly be expressed with multiplication and division in arithmetic. For shift operators, they also have a standard arithmetic interpretation. For example, left shift, you multiply by 2 to the power of the second argument. However, 2 to the power of something is not an operator that is supported in or common in SMT solvers. However, if you look, for example, in the left shift, then most of the values for the second operators don't matter, because if you multiply by 2 to the power of something that is greater than k, and then take the modulo over 2 to the power of k, the result will be 0. So the only relevant values are 0 to k, and k is known because this is the bit width. So we can encode this using, again, ITE operators to all the cases between 0 to k. For bitwise AND, we just use the newly introduced IAND operators, where k is specified by the bit width. And the other bitwise operators, or BVOR and BVXOR, are eliminated using these identities. So that's the conversion function, but notice that in this conversion function we introduced new symbols. We introduced integer variables, and we introduced these IAND terms. So, and there is an implicit assumption about them. As I said at the beginning, every bit vector variable has a sort or a type from which you implicitly know what is the range of its integer interpretation from 0 to 2 to the power of the bit width. So we need to make this implicit assumption explicit, and this is what we do in this lemma. We recursively traverse the formula, and every time we reach one of these terms, we add range constraints regarding it. Okay, so that's the first step, from bit vectors to the extended theory of integers with IAND. And now for the second step, from this extended theory to integers and uninterpreted functions. And I'll present 4 variants of this translation. On the algorithmic side, we have an eager translation that computes the entire formula up front, and the lazy translation that does it incrementally. And in each one of these, we have 2 encodings of the IAND operator, one that relies on the usual interpretation of bit vectors as sums of powers of 2, and the other one is done by just equating the various bits in the bit vector representation of the integers. So in total, we get 4 variants of this. So let's start with the eager variance. So the eager variance is, again, just a function, a translation function t, but it is parameterized by a, whether we use a sum encoding or a bitwise encoding. And the output is just the original formula, the original extended formula with arithmetic and integer and IAND. And we, of course, then consider IAND as an uninterpreted function, and we add lemmas that encode its semantics. And the lemma only needs to encode properties of IAND, so only in the case where we reach an IAND formula we add it. And this is the lemma that we add for sum. It is a sum of powers of 2, where it is all of these powers of 2 are multiplied by either 1 or 0, and the decision is based on whether the ith bit of both of the inputs is 1, and in this case we multiply by 1 and otherwise by 0. And accessing, this is an integer, there is no such thing as an ith bit of an integer, but there is an ith bit of the bit vector representation of an integer, and this notion is definable in nonlinear integer arithmetic with the formulas here of AI and BI. So this is the sum mode. The bitwise mode is similar, but instead of using a sum, we just compare each of the bits to what we expect, each of the bits of the result to what we would expect, that it would be 1 if and only if both of the inputs was 1. Okay, so these were the eager variants, and the lazy versions are based on a counterexample based abstraction refinement on a Seeger loop scheme that we have here. We start with gamma, which is just a translation from bit vector to the extended theory of arithmetic with IAND, but we treat IAND as uninterpreted function. Delta is just a collection of all the IAND terms, and lambda is a set of lemmas. Prop of delta are basic properties of this operator, and then I and A are lemmas that completely capture the semantics, exactly say what should the result be for every input. And it works as follows. We assume that we have some decision procedure for some solver for UF near for nonlinear arithmetic and uninterpreted functions. And first we check whether the abstraction is unsat, where we treat these operators as uninterpreted. And if it is unsat, then we can safely return unsat because it is an abstraction. However, if it is sat, then we ask the solver for a model, and we check whether the model satisfies the lemmas. If it does, we can return sat because then we know that the I-AND operators are interpreted correctly. And otherwise, we add lemmas. We add the lemmas in the places where we failed, where the model didn't, the lemmas that the model didn't satisfy. So on the left, we have the two sets of lemmas marked with blue, and on the right, we have them defined. So the prop of delta are just basic properties, like that the I-AND of two inputs is at most each of them, and it is an idempotent operation and symmetric, and some special cases for the extreme values. And the second set of lemmas, the I and A, depends on the mode, whether it's sum or bitwise, and it is similar to the eager variant, just encodes the meaning with sum or with bitwise comparisons. To conclude this step of the translation, notice that both modes utilize both the SAT solver and the arithmetic solver. Even the bitwise mode needs to access the ith bit of x, which is done with arithmetic means. However, the bitwise mode relies more on the SAT solver, while the sum mode relies more on the arithmetic solver because it introduces sums. And I will conclude with an evaluation. So all four approaches of IntBlasting were implemented in CVC5, which is the successor of CVC4. The first step is an eager translation to the intermediate theory, and it is done in a pre-processing pass. And the second step, in the eager mode, it is done in the same pre-processing pass, but in the lazy mode, it is done with a specialized I-AND solver inside CVC5 that implements the Seeger loop that I just showed. For evaluating, we compared to the following tools. Bitwise and Yikes were the two best SMT solvers in the SMT competition of 2020 for bit vector formulas. And we also used CVC5 Eager BitBlaster because this is the default solver in CVC5 for solving bit vector formulas, and our implementation is inside CVC5. The graphs that I will show also contain results for BWIND, which is our past work on Bitwise independent properties. It is a prototype implementation, but I will not focus on it. And we tested these tools and IntBlasting on 3 sets of benchmarks: SMT-LIB, rewrite rule candidates, and smart contract verification conditions from Certora. Let me describe the benchmark. So SMT-LIB, we just took the QFBV family of quantifier-free bit vector formulas. There are over 40,000 benchmarks that are very diverse. However, not many of them have large bit widths. The second set of benchmarks were handcrafted by us to evaluate our approach. However, they do represent a real application, namely finding rewrite rules in SMT solvers. And we generated the benchmark with syntax-guided synthesis. We synthesize pairs of terms that are equivalent for Bitwise 4. And we want to prove that they are correct for larger Bitwise because only then they can be used inside SMT solvers. So we generated over 5,000 rewrite rule candidates using this approach, and we instantiated each of them with 10 different Bitwise from 16 until 8,192. So we have almost 55,000 benchmarks in this category. And finally, we received from our collaborators in Certora 35 benchmarks. Certora is a smart contract verification company, and these benchmarks are quantifier free with uninterpreted functions and bit vectors with 256 bits. They employ both arithmetic operators and bitwise operators, and they encode algebraic properties of low-level methods in Solidity. So here are the results. I will get into more details about them, but already we can see that for SMT-LIB, our approach, the IntBlasting approach, is not competitive. However, with the other two benchmark sets, it is. So let's see, for SMT-LIB, the experiment ran for 10 minutes for each benchmark. And as I said, the results are not competitive, and this was expected because it is pretty hard to beat BitBlasting on this family. I will note, however, the third column marked UNS, it's for unsat, so there the gap is smaller than BitBlasting approaches, while in SAT the gap is pretty big between IntBlasting and BitBlasting. So I'll continue to the next case study of the rewrite rule candidates. So in this category, all the IntBlasting approaches were better than the BitBlasting approaches. And for this, we also have a more fine-grained results. So we divided the rewrite rule candidates to two sets. Some were included the BV-end operator and some did not. So we'll start with the ones that included it. So the IntBlasting approaches are in red. So we can see that the best IntBlasting approach was a lazy with Bitwise mode. And starting from Bitwise 512, it is the best overall. So you can see that the BitBlasting approaches that are in gray, as the Bitwise becomes larger, then they solve less formulas. The timeout here was 5 minutes, while you can see that this lazy Bitwise approach, the IntBlasting approach, is almost Bitwise independent. The Bitwise doesn't affect how many formulas it solves. Now without BVN, then all the four IntBlasting approaches are the same, and all of them are almost Bitwise independent, and they become the best approach on this benchmark set, starting from Bitwise 122. And combined, the best configuration, the best IntBlasting configuration is the best, starting at Bitwise 256. Finally, from the 35 benchmarks that we received from Sartora with 1 hour timeout for each benchmark, the IntBlasting approaches solved the most benchmarks, and it was also the fastest. Out of the 24 that were solved, 22 were solved in 1 second per benchmark. So here I'll conclude. We've seen that IntBlasting is a complement to BitBlasting and especially useful for large bit width. And we study 4 configurations of IntBlasting based on eager or lazy mode and some bitwise encoding. In the future, we plan to study abstractions of other operators, for example, shift, perform more benchmarking, and improve nonlinear integer solvers, specifically for benchmarks that come from this translation. That's it. Thank you.
Thanks, Yoni. Okay, so is this, Victor, is this question for Yoni? So you want to ask it? Okay, I'll ask it then. Do you think using alternating automata would provide another useful translation target for these constraints, as in verification of data paths using unbounded integers, automata strikes back, or mono?
Sorry to say, I am not familiar with this work, so I can't answer, but I will definitely write it down and look.
Okay, yeah. So, this tension between the kind of integer interpretation of bit vectors and integer constraints, actually goes back to the 90s. Now, in the SMT-LIB benchmarks, you didn't really give the finer grained analysis of when the Int-Blasting approach is superior. I mean, that right. Are there examples where it is superior, and what do those look like?
Yes. So first of all, regarding, I'm not sure if you refer to the work on RTL, the MATSAT people with integer-based
No,
approach.
no, actually, this was yeah, this is the very first paper was written on bit vector solving.
Mm, okay.
This was a kind of design decision, but the work that was done at that time and a number of the solvers actually had this tension that the bit interpretation interferes with doing arithmetic constraints, and the arithmetic interpretation does poorly on the bit constraints,
Yeah.
bitwise
Oh,
constraints operators. Yeah, so so it would be interesting to actually be able to tell from perhaps a profile of the problem, to be able to tell which interpretation would be superior.
yeah. I agree. So regarding specifically for SMT-LIB, we do mention this in the paper. The only family where in SMT-LIB where IntBlasting was better was Sage 2. And we couldn't find why, what was so special, and it was not on the entire family. It was on around 18 benchmarks of this family. And in any case, this family is not stable. It is known that solvers with different seeds perform different on it. So on SMT-lib, we only have little wins and not a good way to explain them. But we do think that more generally, and I think as exemplified in the rewrite rule benchmark set, larger bit widths are good candidates for cases where it is better to do integer reasoning than bitwise reasoning.
I mean, maybe not. I mean, if it's really a larger bit width and a bit vector problem, the integer interpretation might also perform poorly. So it'll be
Yes, it would also depend on the operators in the problem and on the structure of the problems. Yeah, so we tried the way we tried to answer this question partially for now is by this case study, these three case studies, but there is more to be done, and we are also at least in the CVC5 architecture, it is possible to decide what to do after you process the formula. So and even in the lazy bit vector solver. So it might also be possible, we didn't try this, to split the problem and solve parts of it with integer reasoning and other parts of it with bit blasting. However, the main challenge there is that if you split the problem and it has shared variables, then it is a very expensive operator to translate a variable between integer and bit vector.
looks like we have a in-person question. So go ahead.
You mentioned well, break from the Hector's Delight, and I wasn't really sure because it was shown very briefly, but could you explain what it was and why it was used?
I apologize, I couldn't understand the question.
Yes, you have shown on one of the slides a bit trick from Hacker's Delight, the book, and could you explain why it was used in this case?
Yes, the Hacker's Delight book. Um, so we only handle, we only focus, there are several bitwise operators in the theory of bit vectors, and we decided to focus only on one of them. And the reason it was possible is because you can reduce the other ones. So I showed two identities, one that can reduce bitwise OR to bitwise and BV plus, BV add, and the other that can reduce BV XOR to BV OR and BV AND. And that way we can only focus on BV AND.
Okay, it's clear to me now. Thank you.
Thank you for the question.
Okay, any other in-person questions? By the way, it's nice to see all of you. This is great to have the camera pointing at the audience.
Questions right now.
Okay, so thanks a lot, Yoni, for the very clear